How we handle the large amount of data in the online platform and facilitate management and analysis. So we're lucky enough to have three of our own speakers here. Dr. Jinha Jung from Civil Engineering, and we have Jarrod is a ag data service, and we have Ben is working with Jinha's group. So without further ado, I'll let the stage be yours.
Thank you very much. Thank you for all coming to this seminar. And I'm very excited to see pretty good attendance in today's meeting. And today we're going to talk about digital forestry online platform for big geospatial data management analysis. And I'm going to say that I was just cheerleader, just encouraging other colleagues to do the great work, exciting work. And I'm going to just opening up this presentation within the first two slides, introducing two speakers who's going to run this show. And I'm going to come in later to demonstrate some of the latest development that we're working on, and which is going to be very exciting for most of you guys. And like I said earlier, there's going to be a team presentation. Jarrod is going to start off this presentation with the challenges and the potential of big geospatial data. And Ben is going to come in and introduce. We just came up with this the name for the platform that we're developing called Data to Science Engine, which is mainly data-driven the development, or how we can turn those data-driven model into actually science. And Ben is going to talk a little bit about this online platform at about 10-20 minutes. And I'm going to come in at the last stage where we're going to talk about how we can actually consume this big geospatial data in an open way. So with that, I'm going to bring in Jarrod. Come here to talk about
his part.
Yeah, his part.
Cool. Thanks, Jinha. So, it's really exciting to work with Jinha and Ben and some of the others in his group on this system that they're putting together. I'd like to quickly point out some other folks from the Ag Data Services team who are working on this. Nathan Denny in the back there is working on some of the backup for all this data, so that when researchers put their data in the system, they can feel confident it's going to be there. And then Benny's been kind of lead on some of the digital forestry and the data curation and data access. And so that's a big focus of that has been the metadata side of things. So, how do you find the data? What is it? How do you use it when you get it? But instead of talking about those things, since I'm at the beginning, what I'd actually like to do is talk about why this is so important and why I think it's cool. So that way, when you see Ben and Jinha talk, you're like, wow, this is going to change things. Hopefully, I accomplish my goal. And so to start off here, we're going to look at why high throughput phenotyping is important for digital forestry, right? And so some of the challenges that they're looking at are related around inventorying trees. And how can you manage forests, right? And so obviously it takes a while to walk out and hand measure and count all the trees. So those are some of kind of the straightforward and easy to understand areas where digital system sensors would help with forest management. Looking at things like tree health and tree quality, you can use certain sensors to look at the 3D shape of the tree and how straight it is, and how good the lumber it might produce would be, or things like how is disease impacting this forest, or if you have the data on this region. And then we get into things like disturbance monitoring. So clear cutting, areas of forest, how does that affect the wildlife or the water quality, things like that, or a fire came through and it took out these trees, some of these survived, now what, how can we plan to, assist that forest in coming back naturally. And so you can imagine looking at phenotypic traits of trees is an important part of helping forest managers or, forest users, like some of us probably are, make better decisions. And so one of the things that uncrewed aerial systems do is they make it easier to collect data. So you don't have to schedule a time for a plane to fly over with a sensor, or you don't have to rely on the frequency and resolution of satellite imagery. You also have the benefit of a wide variety of sensors that can be switched on and off of these platforms, or they're pretty small. You could actually probably maybe borrow one from a friend here at Purdue. And then finally the scale, right? So compared to going out and a person going out and measuring things, these are obviously these kind of systems and sensors are going to cover much larger areas, and then they're going to be higher resolution typically than aerial satellite platforms. So what makes this data challenging? Well, it's big, and I'm going to provide some kind of comparable context towards the end of this year, but often when people talk about big data, they talk about volume. So, how much data is coming in, how much disk space does it take up, right? They talk about velocity, does it come in every day or every hour or thousands of seconds, right? That kind of thing. And then we look at variety, in terms of the sensor systems being used here, you've got typically a GPS unit on everything so that you know where it was taken on the Earth and you know what time it was taken. And then from there, that's coupled with other sensors. So typical, visible RGB data, hyperspectral data, 100, 200 bands worth of information there. It's been to the point maybe for a while now where LiDAR is small enough to put on these systems and capture 3D data that can actually penetrate the canopy. And I could go on a couple more. There's probably others in this room that could go on longer and longer about different sensors that you can put on here. But that variety is really important, right? And that's just the raw data, right? So, you go out and you scan a forest using a LiDAR sensor, that's a bunch of points that you can't make a lot of sense of. So, you turn those into surface models or canopy models or tree structure models, things like that. So from this comes different data products. And then, I said on campus, there's many producers of RGB data. And that's both a benefit and a challenge that I'll talk about in a minute here. But looking at volume, because, people say big data, you're thinking size, right? Well, if you look at this kind of 100-acre plot here at Martell, it's the highlighted area on the map, or the image, it's not, I wouldn't quite call that a map, on the right. You can see the roads there, you can see some little white squares, those are houses. That kind of gives you an idea of how big the area is. That area can be flown in about 4 hours, and if you have 3 sensors on the platform, you're going to have about maybe a gigabyte or so of RGB data, around 10 of hyperspectral, and half a gig of LiDAR. And you notice at the bottom there, have a completely unrelated thing, which is how many tweets are produced in 4 hours, right? So in about 4 hours across the globe, it would take 8 gigs of storage to store all that, right? And so you can see here, just this one field, one time with 3 sensors is already going to be bigger than that, right? So volume, no question, this is bigger data if we're going to get into that. But I would also say that the Twitter or X data is easier, right? Why? Because it's in a standard format. The knowledge contained in it is sort of well defined and known, and because you can go to one place to get it, right? And sure, there's areas I'm sure where that data is more challenging, right? But those are the 3 I picked. And the reason I picked those are because what Ben and Jinha are going to talk about later really address those issues. And those are critical for being able to collaborate, share data, collaborate on research and analytics within that data. And another thing that's kind of critical to this, we talked about the scale of these efforts. The digital forestry group is 20 plus faculty, so multiply that by 3 or 4 to just postdocs, students, grad students, staff working on this, right? So And that's just at Purdue. So in order to kind of solve some of these challenges that they're looking at, you need a big group of people to work on that. And what that means is they need access to processing techniques, tools, scripts, things like that, and they need the data to use as well. If you think about it, we all rely on a lot of open source software to begin with, right? Like Linux is running the vast majority of servers that power the cloud, the web, that we use on a daily basis. And then in the research space, I think, raise your hand if you're using R or Python or some other open source scripting software language, right? So we count on these things, for our day-to-day lives and also, the research that we do. And so to me, it only makes sense that, we kind of continue on what's been given to us and kind of work with others and help where we can, right? Some data is confidential, can't be shared, code, things like that. But in general, that's, kind of one of the main things that open science professes. Looking at, the why open science here, I think two of the big things that are important here are the blue on the left, the innovation, right? And so that's solving new research questions. And then the quality and integrity piece, right? If the science, if your methods, if your process are open, others can look at it, they're more likely to trust it, right? And what good is all our work if nobody trusts the output, right? So I mentioned that, open science, the kind of two pillars are open software and open data, right? And so for this, we're going to focus on the open data piece of it. And I really like the FAIR principles. I know, some of you were like, oh, and some of you were like, what the heck is that? It took a while, but the idea of your data being findable, accessible, interoperable, and reusable is really important. Reusable data is great, but if nobody else can find it, so what? Somebody finds your data, they can't use it, so what, right? So that's why kind of all these pieces are important. So findable, what we're talking about here is globally unique IDs, and the data is registered in some place where people can find it. In terms of accessible, that means that there's standard access protocols so that it's not a different thing for every different piece of data. And when necessary, the access to that data is limited. In terms of interoperable, the data should be stored in a software agnostic format, right? So not something that you have to have, Windows 97 and some weird application to open. And then once you get the data and dig into it, it should be stored in a way where the knowledge representation is well defined and well understood so that people can make sense of what's in the file. The final piece, reusable. And that detailed provenance, that goes back to the idea that, okay, great, I've got the data. Do I trust it? Do I understand what it is? And so that's why the provenance is really important. And then the usage license, right? If you put in all this work to collect data, you're certainly going to want and deserve credit for that. And I know the funding agencies probably do too. So we'll benefit there. And this last piece kind of ties into what Ben and Jinha are going to talk about. So one of the underlying themes of fair data is that data must be machine actionable. So that means that, yes, we're going to be the ones driving what the computer does, but it can't be a manual process like the old card catalog. It doesn't matter how good your organization and things like that are. With this amount of data, spread across the world, there's no way you can sit down and find it, each one individually. So now to show you how we're going to do that, Ben's going to come up here and talk about the data to science engine.
Yep, so I'll be talking about Data Science Engine, which is an open source platform that we're working on. And these are kind of the list of the key features that we want this platform to have. First, our goal is for this to kind of serve as a one-stop shop for researchers where they can upload their data, manage it. We want to provide the tools so that they can easily collaborate with other team members and easily invite other people outside of their own team and organization into this platform so they can also have access to this data and see how to start working with it. And then also providing tools so that you can do some processing with the data once you're in that platform and you can visualize it in numerous different ways. And then lastly, one of the big components is giving you a streamlined way of publishing that data into a central catalog where it's now discoverable not just from your own internal team, but from the public in general. So to accomplish that, this platform basically has two major components. So we have an application instance and the public central catalog. So the application instance, for most people, this is just going to be a web application that they're interacting with in their browser. They're just going to go to that website, sign in, they'll join a team or create a team, and they'll have then access to the data associated with that team, or they can start bringing their own data into the platform. But as we were talking about, we also want to make this an open source project. So we're going to be releasing the code for this application instance with the idea that anyone can host their own application instance. So there's not going to be just one of these sitting on a server at Purdue, but anyone will be able to download this code and launch their own application. And so that's what I mean by open source and self-hosted. We want this, you can download it freely, and then you can host it from where you like. And to kind of help with that process, we're containerizing the whole application. So a web application obviously has a full stack of software that's supporting that application. So we have the front end, back end, the database, web server, all those components. But we're going to be using container technology to kind of make that process of getting this up and running yourself as easy as possible. And I'll explain that a little more on the next slide. And then the other major component is this public central catalog. So this is where all these different application instances are running. Everyone will be able to publish data into this one central catalog that's publicly discoverable with no accounts required. Anyone can just go to this catalog in their browser and start looking at what data is out there and available for them. So a little more detail on how we're designing this application instance. So like I said, the entire application is going to run inside containers. And the benefit we get from doing that is you do not need to have a background in the back-end framework that we're using or the front-end framework we're using. You don't have to worry about, is the database that we're running matched the same version that might be on your own server. All this is going to be isolated inside containers, which is going to make it highly portable. So basically, we're using a container technology called Docker. So if you can interact with Docker, you'll be able to get this application instance up and running. You don't have to mess with any of the internals of these containers. We'll be providing all the instructions that Docker needs for building the exact environment to support the application. So that's why I say it's highly portable, because I run this on my personal Linux laptop, but you can run it in Windows, you can run on Mac. You can take these Docker images that get built and run it in a cloud environment such as Kubernetes. So basically, if it supports that container technology, you'll be able to get the application up and running. And the one last important thing I'll mention about the application instance is all the data that you put into this will remain within that application instance and where it's being hosted. None of the data that you upload is going to be ever leaving that unless you fully intend to, as when you're publishing to the public catalog. So for the public catalog, so this is where all these application instances are running. We'll be able to publish data into. But I'm saying data, but it's actually going to be metadata that they're publishing into this catalog. The actual physical data set, so let's say you uploaded a orthomosaic and you want to share that with the public catalog, you would only be sharing metadata describing that data set and how to access that data set through a URL to this catalog. So the physical data will always remain within that application instance. And so once you publish this catalog, we have a few key things we want you to be able to do from the catalog. Obviously, be able to browse the data, but also, since all this data has a spatial and temporal component, be able to search by space and time, and also be able to filter down to specific data types. So let's say you're interested in data from Tippecanoe County from 27 to 2022, and you're primarily interested in orthomosaics. So you should be able to fine-tune your search within this catalog so that you only see the results relevant to that space and that time frame and that type of data. And lastly, you should be able to visualize the data in that catalog itself, view the metadata for the data, and have a clear path to how you can start incorporating that into your own workflow. And so to achieve this with the public data catalog, we're using a specification called STAC. It stands for Spatiotemporal Asset Catalog, and it is a metadata specification. It's organized into primarily 3 data models. At the top level, you have a catalog. Then within a catalog, you can have collections of similar types of data sets. And then at the lower level, you have an item, which can be an individual data product. One of the appealing things about Stack is it's a very kind of bare bones specification. You have to have a spatial component, you provide it, and a temporal component. But outside of that, it doesn't ask too much from you. But at the same time, it's highly extendable. So if there's some metadata that you find is very important for your type of the data that you're putting into the system, there's going to be a means for adding that metadata into the Stack catalog and expanding on that specification. And the other great thing about Stack is it's got a ton of community involvement. As they are developing the specification, they are also building tools that can work with that specification. So there already exists a web application that can make a Stack catalog, so all the metadata in the Stack format into a browsable catalog. There's also a Stack API for implementing API to make it possible to query Stack metadata to find specific data sets by space and time. So all that kind of infrastructure is already out there, so we can, and it's also all open source and freely available to use. So we'll be able to pick up where that is at in the community and start bringing it into our own platform and expanding on it. And so just a quick example, just to show what Stack metadata looks like. This is the metadata for like a single Stack item. You have a Stack version, type, ID, then it wants a bounding box, geometry. So if it had more complex geometry than just a rectangle, you could give, say, a GeoJSON describing that geometry. Properties is where you can put in information such as the date that the item was collected, or if there's a range of dates, you could provide it there, along with any additional metadata that's important. Identify a collection it belongs to, and then with that asset property, that's where you can provide the URL to how to actually access that Stack item. And we've already been working on a Stack catalog, and I think we'll have a demonstration of that later. And then here's this kind of big picture, how it all comes together. Over on the left, we have like an application instance that Purdue is hosting. Then down the bottom middle, we have another application run by another group. Could be anyone. But the key thing is that both of these application instances are all contributing into that one central data archive that's kind of powered by that Stack specification. So now, though, I'd like to switch gears and actually just demonstrate where we're at in the development process. We're approaching what we're calling version 0.1. So we're still working with our UI, UX team to improve the look and the experience from the user perspective, but we've already implemented a lot of the key features that we think are necessary for this first version. So that's what I'm going to demonstrate now, is where we're at. Yes. So this is our landing page. So you do need to have an account to sign up and to start using the platform. We have a very simple registration form, just first name, last name, email, and password. And the reason you need an account is because we're going to be providing tools internally in it for collaborating with other team members and stuff. So we need some way of identifying who's on the platform, what teams they belong to, and what data they have access to. I will go ahead and sign into my account. So once you sign in, you're going to see a map, and then over on the left, you'll see all the projects that you have access to. Assuming you already, if this is your first time signing in, you'll be prompted to go and create a project or join a team. But before I get into the projects, one of the first things you might want to do when you sign up on this platform is if you already have someone else in the platform that's created a team and they've already uploaded data that's associated with that team, you could come to the Teams page, you're invited to join a team, and at that point, you would then have access to all the data associated with that team, and it would start appearing on that homepage for you. Or if you want to get a team started, you can come to the Add Team page, provide a team name, team description. You'll be able to invite anyone that's already on the platform to join your team. And then if you already had a project that you've been uploading data into, you would be able to assign this team to that project. And again, all the team members would then have access to the data within that project. So the next step you might take is creating a project. So on this workspace page here, I can see the 3 projects that I currently have access to. If I wanted to create a new project, click Create here, provide a title, description, and then a geographic boundary of where the data that's associated with this project is contained. So typically that might be like a field boundary, which you could upload as a shapefile or digitize on this map. And you could associate this project with a team. So if you already had a team in mind that you wanted this data to get shared with, just select the team at this stage. So once you've created a project, though, you'll be able to open the project. And so once you're on the project page, this is where you can start adding flights. Because again, we're working with right now UAS data. So basically, every time a flight's flown, you'll be able to add that flight to this project page and then upload data that was collected during that flight. So here we can see we have 4 flights ranging from June 4th, 2022 to August 20th, 2022. And you can identify the platform, the sensor, and when you're adding, you can also set the altitude, side overlap, forward overlap, and select a pilot from your list of team members. Once you've created the flight, this is where you can start uploading data onto the platform. So if I go to this flight here, we can see one data product's already been uploaded in OrthoMosaic, which we have a preview of. But right now you can upload 2 types of data, or 2 broad categories of data. We have an upload for raw data. So all the individual images that are captured during the flight, you can put those in a zip file, upload them here, and then they can be retrieved by any team member at a later date if they need to work with those. We also have several data products that we support right now. You can upload a DSM as a geotiff, OrthoMosaic as geotiff, and then a point cloud. And one of the cool things we do, whenever you upload a geotiff, so DSM or ortho, while that's uploading, after it finishes uploading, we're going to start a worker process in the background. And what that process is going to do is convert that geotiff into a cloud-optimized geotiff. And if you're not familiar with cloud-optimized geotiff, it differs from a regular geotiff in that it has internal tiles and internal overlays. And because it has that internal structure, we can use HTTP range requests to basically request just the portions of the data set that we need for what we're viewing on our map. So based on our zoom level and the extent of the data and what we're trying to do, it'll be able to extract from that cloud-optimized geotiff just the data that's required. So, but otherwise, it's going to remain as a single file geotiff with a .tiff extension. And same with if you're uploading a point cloud, we're going to convert that into what's called an entline point tile, which is another format that we will then be able to ingest with a third-party library for displaying that point cloud inside the web browser. With that, I will switch back to the home page to show how this all comes together. So if I go to this first project here, we can see that 4 flights were added to the project. See what dates they were flown, and each of these flights have 2 data products within them. So I'll go to this first one here. So we have an OrthoMosaic and a DSM. So this was around, I think, 2 gigs when I uploaded that file. So what we're using is that cloud-optimized geotiff format, and then we're running that through a dynamic tile service to display the tile layer on the map. And we can see that it's very responsive. Those overlays come in first, that's a little lower resolution, but then as you zoom in, give it a second, and it starts, the higher resolution imagery comes through. And so it's very responsive. And the other great thing, since we're using that dynamic tile server, we can apply on the fly changes to color properties and to the range, so min and max values of these data products. And we can also change the band order. So with an OrthoMosaic, let's say if you had a 4-band data set where you had a near infrared band and you wanted to switch these default band assignments, you'd be able to come in, make those adjustments, click apply, and then on the fly see those changes on the map. Similarly, you can change the min and the max value. You can use a user-defined min and max, or you can use the mean plus or minus standard deviation. I'll switch over to our DSM. So with the DSM, you'll have the option to change the color ramp. So I can go to this list here. I'll choose red, purple. Click apply. We can see that color ramp applied. And then we can also adjust the min and max values. I can come down to mean plus or minus standard deviation, and then 1.5 here, apply. And we can see those changes immediately reflected on the data tile layer. And if you want to come back to this at some point, so you want to see this view every time you return to the site, we can click save here. So now when we come back to the page, open up that data product, we're going to see the last symbology settings we were looking at. Another visualization tool we had recently added is this compare tool. So if you're interested in looking at two different data sets for two different time periods and seeing how the changes between those two times. Over here on the left, I'll change this to Saturday, June 4th. And I'll change the one on the right to June 23rd. So we can use this slider now to see that comparison between what we had on June 4th to June 23rd. Switch it out, it'll stay in the same place and compare that. So the last thing I'd like to show off is, so that was with our DSM and orthomosaics, but we can also visualize point clouds on this platform. So this was taken, I believe, in October 2023 here at Purdue, the Push Center. And so here's our point cloud. And again, I think this was around an 8 gigabyte data set that we converted into that Entwine point tile. And we're adjusting that with a third-party library to display it in the browser right here. You can zoom in. There's tools over here for making measurements and that. But yeah, I think that's where we're at in the development now, and a few more things to demonstrate.
Okay, thank you, Ben. I'm going to switch my screen to my laptop because there are certain demonstrations that I'd like to do.
Let me make you the copy.
Yes.
You should be able to now.
Okay. Can you stop sharing?
It's okay.
No, do I have to stop sharing from here? Sharing here.
Yeah, it's like that green and blue circle.
It's Microsoft Edge.
Okay. Desktop. So,
So you're not seeing it.
laptop.
It was it for there we go.
Okay, so Ben showed that the actual online platform, but the other important piece that we talked about is in the central catalog. We built a central catalog where we can actually find the data during the spatial temporal query, but the bridge between the actual instance and central catalog has not built yet. So keep that in mind, but in the future, when you have this instance being deployed, you're going to have a full control of which data set that you're going to keep inside the instance, which data set you're going to publish. There's going to magic button there, publish, and that the metadata will be pushed back to the central catalog that I'm going to demonstrate right now. And this is a website that probably a lot of you already know. This is a website where you can search for Indiana statewide LiDAR data that has been collected twice by now. And I'm not going to demonstrate this because this is the one basically that is consuming exactly the same stack catalog that I was talking about earlier. And the one that Ben mentioned about is that good thing about stack is that there's a very rich user community where they're developing very good tools. And the stack browser is one of them, where once you have a stack catalog, we can turn this into our the web browser application where you can do search over here. Another thing that is running behind is that Stack API, and we're using something called a PG Stack, which uses a PostgreSQL database in the backend. And whenever we just do some kind of query, that query is going to happen in the database engine. That you can just look at the query at the end over here. But if you go to the stack.digitalforestry.org, this is the public website where you can do search and everything. This is a catalog. You see all this data collection over here. We have an Indiana GS data harvest collection, LiDAR DSM collection, NDHN collection, and ETM and ortho imagery collection over here. And we can just click through it. For example, if I click this ortho imagery, I can just click this one here. That you're going to be able to see actual Indiana ortho mosaic imagery. This is one over, I'm going to say over 200 gigabyte. And you can see how quickly it just show up. It is because all those cloud optimized data format is sitting behind it. So we can just search by in this way. But another way of doing it here is that the button called search. And you can do, temporal, the query over here by specifying from when to when I like to, find the data. Or I can, the filter by the spatial extent. I can just, zoom in here, just zoom in all the way in. I'll zoom into Indianapolis area because Indiana auto imaging for Indiana County has not been published yet. But if I just zoom into this area, these are the areas that I like to, to search and a quick filter, then that it will show you all the data product that is available for the specific area that we're looking at. And some of the, I think already demonstrated that, ortho mosaic imagery, but you see that all the other data product is available. You also have Indiana JS data harvest layer. This is the vector layer that is managed by Indiana Geographic Information Office, and they release this data set every year. And downloading this data set takes a lot of time, but the good thing about here is that we are storing all this vector layer into vector tile layer that is cloud optimized. So you can just click this and open in PM Tile Viewer. Then you're accessing this whole data set. And just turn on parcel layer because they're using this vector tiles. They are not showing all the tile at this zoom level, but as soon as you start to zoom in and you zoom into Lafayette area, you're going to start to see that all those parcel layer is going to start to pop up. And if you just click show attributes, you have all those attributes also available over there as well. Okay. How can I hide it? I don't need this. So this is a stack, which is in a great, but stack is in a great resources where you can just go look for the data. But the good power of this open data or open science is that we don't need to limit to certain software. This is an open. This can be incorporated into any other software that knows how to consume this in a cloud optimized data format. So what I'm going to demonstrate next here is that it has a pretty good support for Python packages. So there, open source library, for example, the one that I'm using over here is in a leaf map where you can actually consume all these, the cloud optimized data format inside of Python. So I'm not going to go through it, but there is PM tiles layer over here, doing some the query over there. The one that I like to demonstrate is the bottom one here. This is the actual code to generate this map at the bottom using Python. But I can just zoom into this layer, and you will start to see that the same the vector layer that I was talking about. You can see the parcel layer. You can see the address point. World center line, everything, we are just only streaming the part that we're looking at. And we don't need to download the whole data. We only need to stream the portion of the area that we are looking at. So we can, this cloud optimized data format has a pretty good integration with Python. So if you're just in a Python programmer, you can just start using it right away. Another tool that I like to demonstrate here is that we also integrated this into the QGIS environment as well. So that, for example, if I like to do this one, okay. And if I like to integrate this into, for example, in a QGIS environment where we developed a plugin where it is essentially consuming this stack behind it. I like to load. I'm going to just do it in Adams County here. I like to do it in a DTN. You see that I just clicked it. This is over the Wi-Fi. This is probably a few gigabyte of DTN. It just shows them right away. And once you load this up, this is the same GeoTIFF file as like you have in your local machine. You can come in here. You can change the symbology to pseudocode over here, and just do it. They're going to change it right away. I can just do the histogram by looking at here. Mean value should be somewhere around 750. So I'm going to come back here, change the mean value to be 750. Over there, we're going to see much better contrast over there. And I can add hue shaded. There are other data products available over here. I'm going to hue shaded images, put these at the bottom. change this in a visualization a little bit so that I'm gonna do multiply. Then you're gonna see, let me just zoom into some of the area here. You're gonna see that not only color in lambda, but we also see the heat shaded images and overlay. And this is the data that, all this operation that I'm doing is over the Wi-Fi. And we are not downloading this data, we are just streaming only the data that we need to actually, use to see it here. We also have, auto imagery integrated into this one here. So I can just load up the auto imagery for the county here. This is over 200 gigabyte that I just mentioned earlier. It just shows up right away. I can just zoom into the area. Then you're going to see that this is very responsive. They just download this in a portion that we can just visualize in this way. So the point I'm trying to make here is that the power of this central catalog, as soon as publish it, this can be consumed in any open source platform that knows how to consume this kind of data. And the vision that we like to achieve in the next couple of years is that we're going to develop in this data science engine that will give you a full control to manage your own data set. Once you believe that, hey, this is ready to be published, there is a button where you're going to publish that goes to the central catalog. People can come to the central catalog, to find the data. They can just use this data set to do their own research. And we are working on, I'm just demonstrating only the portion that we are working right now, but we are working with other scientists. For example, I know Luis is over here, Diane Wang. We are working with their group so that he already developed, the framework to manage the field data. This field measurement data can be easily incorporated into this one, so that we can incorporate this into this stack catalog and data science engine as well. Of course, we've been, this is the first group meeting. So once we publish this data science engine instance, everybody's more than welcome to contribute your data. And the one last piece that I'd like to highlight here is that whenever I said that open science, it's not just about the data, it's also about the software algorithm we develop as well. So I just did some demonstration of how to do Python programming using this open data set. That code can be also public as well. People can use your code to apply to other data set using stack catalog as well. So what we like to build here is that we like to build an ecosystem where you can to share not only your data set or also your the orders and algorithm or software developed with a much larger public. So I'm going to stop here. And okay, one more thing that I want to talk about, which is some of the statistics about once we started this. This is the diesel first. I like to thank Songlin for giving funding this in the server purchase. I know we purchased it in 2020 early, and that was about $10,000 investment of hardware. And we started this in a diesel Forestry server, and this is the number of monthly user. Number monthly visit for that server over here. We started from somewhere around 208 per month. Latest is in October 2023. We are almost getting 2,000 visits per month. And this is a continuous increase in terms of number of users. And we also have some statistics about how many gigabyte of data is being downloaded from this server. So I'm only showing the statistics for the September 2022. The unit over here is in the gigabyte. So we have about 300 gigabyte. There's some month in March 23, we have a terabyte of data download. And when we started offering this in a cloud optimized data format, I think it was sometime around May, June. And this data volume goes up like crazy. So I'm going to just go to the next page over here. You see that this is the one that you saw earlier. August, of course, I think this correlate with the start of the fall semester. There's a lot of Purdue students probably using it. But October, in August alone, we have more than 10 terabyte of data download from this server. And we went down a little bit, but 9 to 10 terabyte is in a pretty good volume of data service. So there's a lot of people using it. So with this, I'd like to go back to final slide that I'd like to acknowledge. Oh, funding source. Oh, we don't have it here? Or then I'm gonna go back to this screen. Oh, we don't have a funding source. We have it. But I'd like to thank Mr. Forestry for sure, Plant Science 2.0. Those are the internal seed grant that that gave us provided funding to do it. We also had a small seed grant from USDA, which is also this as well. And we recently submitted a couple of proposals to NSF, and we plan to keep submitting proposals so that we can keep doing this kind of development in a sustainable way. So I'm going to end my presentation. More than happy to answer any questions.
I have a question.
So I noticed you said that you're starting with field data. One of the things as an image person, I know that everything's in an array, it's consistent, but field data, it depends on the scientist. And everybody I've worked for has a different field book. So I don't know how you're going to normalize that, or are you going to have just, everybody has their own and then they explain how they store the information, etc.
So I think it's more question to Luis, but he developed a framework. I think it goes to ETL.
ITL and ITC. So there is two tools. The first one aims to standardize the way that we collect data. So to make easier to upload in a similar format in a database. But if not, there is the ETL process that is also aims to standardize the data to be able to upload into a database.
So then you'll go and appear at the agronomy faculty meeting and try to get them to get on board.
Yeah, so we started with our lab, and always there is a resistance to the change. But once they try it, they realize that it is easier to have things standardized than try to fix them and waste time fixing the data instead of analyzing them. Yeah.
And I think the real power will be integrating that the framework into this data to science engine, where you already have a pretty good framework to manage your UV data set. You have a good framework to manage your field data set. Connecting those two in a single platform where you can consume it and visualize it. I think that's going to be real synergy that we can see.
So you showed with your engine there, you showed the remote sensing imagery, and it looked like it was set up largely for that. But could you put in, would it accept soils maps? Would it accept as applied maps for rates of fertilizers and pesticides? It'll handle all that?
Yes, because the example that I demonstrate is that the Indiana data harvest layer, they have a polygon, they have the address point, which is an individual point, as applied. The yield data, they all come as a point data set, so it can be easily incorporated into this framework.
So are the Purdue Ag Centers using this, the PACs?
Not yet.
Oh, okay.
We'd love to work with them, incorporate this. Yeah.
So also weather data can be included with.
Thank you for suggestion. We don't have any plan yet, but that can be definitely a good addition. I know probably work with Beth Hall. She's the one who is managing those weather station for the Mesonet. So that can be a good collaboration that we can develop as well.
That would be pretty cool.
I would say we're not going to be the ultimate host for all of this data, but this can be a good place, at least for you and me to begin with. And then other like soil, and already the host of they also develop their stacks. And so the purpose is to allow this more streamlined, get an unstacked data through this stacked data together. So this is actually my question here. I'm going to ask is that you demoed that this current stack can be pulled into QGIS and other platforms. But that sort of added another layer of barrier for people to use. Or it depends on who the audience and who your population. Is there a plan on the current platform of some easy utilized, like quick tools people can use? For example, like in the server, you already have some built-in tools by the Forestry, like do a profile analysis and do stuff. Are you planning to do any of that in the current platform?
To answer your question, we will, work on it because we are doing that we're going to be the main developer. But the main reason why we are developing this in an open ecosystem is because we like to, recruit the community, so that the people start to use these platforms. They start to build their own, the tools and share those tools with others. And I'm using tools in a very generic way. Tool can be a source code. Tool can be a web application where somebody who doesn't have a programming experience can just use it. Some of the the LiDAR Forestry website is one example. But what they are consuming behind is actually a data source. We can build the application on top of it using Python, or can be in a full stack application as well. So we will develop some of this, but my vision is that I'd like to build an ecosystem where almost like the App Store. Apple do provide the SDK, but there's a lot of developers they're willing to put their time to develop some application and post in the App Store so that people can use it.
My second question is that it's great to see terabytes and terabytes of data being pulled from the server and being distributed. But how are you going to capture that credit other than showing us this being popular?
So there's the how we're going to capture. So this tech catalog will have a record that how many people is using it, and but we are not going to have a full control about once we publish it in the set catalog. If somebody download it, they just create another set catalog in somewhere else. We're not going to have any control. So it's not a easy answer for that one. That at least in the set catalog we'll have all this information about who is the one published it. That we're going to incorporate the DOI into it so that people can actually reference to that data source and such as well.
I think you should work with at least others, at least within the university, others too. Because I'm using Iman for example. Iman created a wonderful set of data, decide deposit. If there's no credit coming back to a contributor, then obviously you want people to use, but meanwhile you also want to provide credit for. So it's like the clear system, at least the DOI is always associated with the data set. If you agree to download and use the data, there will be in the DOI, and you're going to have a citation associated with it.
Yeah.
So something has to be done with that.
Of course.
And even just think about the Indiana LiDAR data. Yes, it is the government paid the data source, but it's you guys who are putting all the energies creating these tiles for this to be distributable. So I think you guys need to be creative or thinking about how to capture that credit, not just counting how many people download, how many.
I just had a meeting with the Indiana GIO a couple of weeks ago, and they want me to submit the proposal to them. So we'll get some credit for sure. And I'd like to highlight one more important person that I didn't include over here, Dr. Cheryl from School of Art, and her group is instrumental in making UI UX usable, because we are engineers. We like to build things, but we don't pay attention about the looks and how simple it is. So we are having weekly meeting with Dr. Cheryl's group, and we've been getting consistent feedback from her group. So I would like to acknowledge her contribution to this project.
Okay, there's a question over there, and
To follow up on
on Songlin's question real quick, what Ben was saying is that you can associate licenses with the stack catalogs. So then at least in terms of like research credit, people should be citing you and that kind of thing. And then obviously monetizing it and paying for it is a separate ballpark.
So I have a, first of all, I want to say it's a really cool tool. I really think that what you built is really useful, and I think it's a great thing to have, especially that you keep the data and you can publish it out. A very technical question. If you're working with large data sets, I believe there's a limit to how much you can upload file size at a time. How, I mean, is that a limitation you run into? And how are you overcoming that? I think you can only upload like 4 gigabytes at a time. So if you're talking about large data sets, does that cause the user to have to break that up and then upload it, and then it can be combined, or?
Short answer is there's no limit. So you can upload as big. I think we tried a few tens of gigabytes.
There's typically default limits, but they're set by like whatever web server you're running.
Yeah.
So like with Nginx, I think it is like maybe 4 gigs is like the cap on it, but there's configurations you can go into to set it to unlimited file size.
So the good thing about this is we are also one who is managing the server, so we have a full control. And I know there isn't a big data, but in my opinion, storage is the cheapest component in all this development. So
I was thinking there was a browser update or a browser limit. And maybe some of my colleagues.
No, you're right, but I think you can, the file upload process, I think like in one like basically like one HTTP, like one transaction, I think you're right, it's limited to a certain amount. And it is configurable as well on the web server side, but the, a lot of the libraries, I think actually will do that like in iterations so that it essentially expands that limit beyond that.
That was one of my questions, you know, did they have to break up in the, whatever the browser limit, 4 gigs or, okay.
There's quite a amount of people online. Do they have questions?
I just checked. There's no questions.
So we are targeting to release version 0.1 by end of this year, and we will have a workshop planned at the NAPPN meeting in February. So if you'd like to learn how to deploy your own instance, how to use it, please come to the NAPPN workshop.
And I want to give Jinha a plug here as well. So you guys all know YouTube, right? And we want to build a YouTube version of the drone data or any drone-based geospatial data. So want to be in a centralized place. Anyone have US data, that's a YouTube place for it. That's his dream.
They make a lot of money as well.
I have a thought.
The ulterior motive.
All right, well, thanks everyone for coming. And this is the end of this year's presentations, and we are going under this